sa video natin ngayon, we'll try to solve this problem involving steel design. However, even if this is under steel design, our method of analysis will involve mechanics, torsional shearing stress, and direct shear stresses. Now here we have a bracket that carries an eccentric load of 200 kN with the eccentricity as shown. Now the diameter of the bolt is 25 mm for the 3 bolts. And so yung first talaga natin gagawin whenever we encounter this problem is we'll first resolve the components of P. Now diba, since this is inclined, then this has a vertical component and a horizontal component. Now taking the hypotenuse of this triangle, we have 12 squared plus 5 squared, which is 13. And so let's say this is our vertical component, which is downward, and then we have a horizontal component which is going to the right. Now again, this is 200 kN. So taking the vertical component, we have 200 multiplied by 12 divided by 13. And so this is 184.62. So 184.62 and then kN. And then for the horizontal component, we have 200 multiplied by 5 divided by 13. So this is 76.92. And so now, after we have resolved this into components, we need to find the centroid of the bolt group. Now, the next question will be, how can we find the centroid of the bolt group? To find the centroid of the bolt group, we're going to use Vergnon's theorem. So this is going to be, in our discussion of centroids, the total area times barred x or barred y is equal to the summation of AN multiplied by barred xn, where AN is the area of interest, while barred xn is the centroid of the area measured from the reference axis. So here, since we have 3 bolts, the total area becomes 3 multiplied by the area of each bolt. So we have here AB. This is the total area. And then we have barred x. Now the reference for barred x and barred y will depend on you. Now here, I'm going to use this line as the y-axis to compute barred x. So we have here the reference y-axis, while for the x-axis, I'm going to use this line. So this is my reference x-axis. Now sir, how do we choose our reference? In choosing your reference, make sure that the line will include a lot of bolts. Now for the reference y-axis, I can actually move this here. However, if this is my reference, I can only include 1 bolt. However, if I'll move the reference right here, I can include 2 bolts along this line. And so this will shorten my solution. And then for the reference x-axis, I can have it here, but it will only include 1 bolt. That's why it's better to put this here. And so we have here AN barred XN. Now here, since all the bolt areas are the same, we can just label it as AB. So we have AB. Now for barred XN, for the first bolt, let's say bolt A, the centroid of the bolt is located along this axis. So that's gonna be 0. So we have AB times 0 for bolt A and also for bolt B, because the centroid of this bolt is also along the reference y-axis. So multiplied by AB times 0 again. And then for bolt C, from this line up to the centroid of this bolt, that's going to be 250. So we have plus AB, the area of 1 bolt, multiplied by 250. And so this simplifies into 3AB times barred x. So this is equal to, this will cancel. And then we have AB multiplied by 250. And so solving barred x, this will also cancel. So we have 3 barred x equals 250. Barred x will be, from the reference axis, 250 over 3, which is approximately 83.33. Now the question is, when will this matter? Solving barred x using Vergnon's theorem will matter if the area of each bolt will be different. However, if the bolt areas are the same, then we can actually derive a formula from Vergnon's theorem. So we have here, let's label this as the number of bolts. So we have N times the area of each bolt, that's gonna be the total area, multiplied by barred x, and then we have AB multiplied by the summation of barred xn. Because if all of these areas are the same, then we have this form. All of these areas are AB, and so that's gonna cancel when we'll solve for barred x. So we can cancel this and this one, and then we have n barred x equals the summation of barred xn. Now this can be barred x or barred y, depending on what you're trying to solve. So this is for uniform bolt areas, which is usually always the case. Kasi as engineers naman, hindi naman pwede na the diameter of this bolt is larger than this one.
that will be difficult to purchase. And so usually uniform yung bolt areas, and so we can just actually use this one. Now to demonstrate this for barred Y, let's try to use this formula. And so let's just replace this. This becomes barred Y, and then we have the summation of barred yn. And then by the way, our barred x is located right here. So this is 83.33 from our reference y-axis. So 83.33. Now for barred Y, we need to consider our reference x-axis. So we have the number of volts equal to 3, and then barred Y is equal to the summation of barred yn. For the first bolt, let's say bolt B, our barred Y is 0 because the centroid of this bolt is located along the reference x-axis, as well as bolt C. Now for bolt A, barred yn is 300 mm from the reference x-axis up to the centroid of bolt A. And so solving barred Y, we have 3 barred Y equals 300. This gives us 100 mm. And so from the reference x-axis up to the centroid, this is 100 mm. And so this is how we're gonna solve barred X and barred Y for our bolt groups.
And so now, instead of placing the load here, we can actually transmit that dito. But then, we'll also apply a twisting moment. Kasi diba, this force, or the vertical component of P, it will cause a twisting moment about the center, and also this one. Now this force will cause this point to rotate clockwise. And then this force will also cause the centroid to rotate clockwise. And so our applied torque right here is clockwise due to this force. Now to maintain equilibrium, we need to have reactive forces right here for each of the bolts. And so to draw the figure, we need to connect a line from the centroid up to the center of the bolts. So this is our first line, this is our second line, while this is our third line. Now the reactive force that will counteract the torque must always be perpendicular to the connecting line. And then the rotation that it will cause must be opposite to the applied torque. And so since this is clockwise, then the direction of this force must be going here. And so this is perpendicular. Now sir, why is it going here? This is because if you will apply this force about the center, then it will rotate this point counterclockwise, which is what we want to oppose this moment. And so here at point C, we also have a reactive force which is going this way. So this is also perpendicular. And then here at point B, we need to have this direction of the force so that it will rotate this point counterclockwise. And so these are now our forces. Now, since we have transmitted already the twisting moment, we can also transmit the load and then place it at the centroid, because the eccentricity is now dealt with by the applied twisting moment. And so now we have 184.62 kN, and we also have 76.92 acting to the right. And so now, if you're to draw the FBD of each of the bolts, then the bolt at A will have these reactions. Now, by the way, there's something wrong with the figure. This must be perpendicular to the green line, not the red line. So let me just rotate this. This is now our force, and this is also perpendicular. Now, our assumption here is each of the bolt will equally carry these transmitted forces. And so this means that for bolt A, we need to have a force that will counteract this vertical force. And so for each of the bolts, that it will have a reactive force of PDY, or a direct force along Y. So this also carries PDY, and also this one, this has PDY. And so to solve this force, we can just divide this vertical force by the number of bolts. And so our PDY will be 184.62 divided by 3 bolts. So this gives us 61.54 kN. And then we also need reaction forces to resist this horizontal force. And so let's say this is PDX. By the way, since this is going to the right, then our PDX must be going to the left. So this is PDX, and also this one, and we also have it here. This is PDX. And so PDX will be 76.92 divided by the number of volts, which is still 3. And so this is 25.64. And so now, we'll try to identify the resulting torque at the centroid of the bolt group. Now to get that, we need to take moments about this point, but we'll still consider the eccentricity. And so taking moments about the center, then we have this vertical force multiplied by this moment arm, which is, in our figure, that's 166.67 plus 200. And then the moment arm of this force going to the center, that's gonna be this distance. And so this is 70 plus 100. And so we can now take moments about this point to get the torque T. So we have T equal to 184.62 times 200 plus 166.67 and then plus 76.92 multiplied by 70 plus 100. And so this gives us 80771.0154, or let's just say 0.02. And then our unit is Kn times mm. And so this is now our torque. And so now notice that these resisting forces for the torque are actually inclined. And so, sir, how can we resolve this one into components? Now, this is what's going to happen. For bolt A, we have PDX and PDY, while this force will have vertical and horizontal components going down and to the right, respectively. And so, let's color this one blue. Our PTY is going down, while our PTX is going to the right. Now, sir, what does T mean? Remember that this stands for direct, letter D. And so T right here stands for the force due to torsion. And so let me just move this one. Let's now try to look at the bolt at B. So we have B, and then this is our bolt. So we have PDX going to the left. So this is PDX. And then we have PDY going up. So this is PDY. And then for our force that resists the torque, we will have a downward component and a horizontal component going to the left, since this is down and going to the left. And so this is going to be our PTY, while this is our PTX. And so now, let's also try to look at the bolt at C. And so at C, we have PDX going to the left, and we have PDY. And then for our PTX and PTY, the components will be upward and going to the left. So we have here PTY, and this is PTX. Now, just some additional input from these free body diagrams. How can you identify the bolt that is most stressed? To identify the most stressed bolt, just look at the bolt where PTY and PDY are along the same direction, as well as PDX and PTX. And so here we can see that for bolt A, PDY opposes the direction of PTY. And so that's not going to be our most stressed bolt. And then here, we also see that PDY opposes PTY. However, in bolt C, the direction of PDX and PTX are the same, as well as PDY and PTY. So this is the most stressed bolt. And so this is a very important concept. Now, sir, how are we going to solve the values of PTY and PTX? We'll try to determine how PTX and PTY are to be computed. Now we have here, for the polar moments of inertia of the bolt group, we have rho squared equals x squared plus y squared. This is from the Pythagorean theorem. Now diba, this was the centroid of the bolt group. Now the distance from the centroid up to the centroid of a certain bolt, let's say that's rho. Now we have here the distance along x and the distance along y, this one and this one. And so by Pythagorean theorem, we have rho squared equals x squared plus y squared. And so that's why this is how we can determine the polar moments of inertia of a certain bolt group. Now x and y here are the distances along x and y of the bolt from the centroid of the bolt group. So again, this is y and this is x. Now for this bolt, for let's say bolt A, this is now our y distance and this is still our x distance. And then for bolt C, this becomes our x distance, this one, from the centroid up to the centroid of C, and then this is our y distance. And so this is a very important concept that we'll use later. Now for the polar moment of inertia, we need to sum up area times rho squared. But since we know that rho is just equal to x squared plus y squared, then we can change this one. So this becomes x squared plus y squared. And so we have here, this is equal to the area of a bolt multiplied by the summation of x squared plus y squared. Now notice that this just resembles the transfer formula, which is A times D squared. However, in steel design applications, we usually treat J as only x squared plus y squared. We don't include the area. We usually only include the area in mechanics of deformable bodies, where we are interested in the shear stress. Now, for the calculation of PTX and PTY, we have the following formulas. For PTX, we have T times Y over J, and then for PTY, we have T times X divided by J. Now, the way I think about this in my undergrad years is this is just similar to the shear stress equals TR over J. Now we know that stress is equal to force over area. So let's say this is PTX or PTY. Now this is divided by the area, and then this is equal to T times R, which corresponds to the radial distance considering the moment arm. So this may be X or Y.
and then divided by j. However, we know that j is just equal to this formula. So copying this one, by the way, since this is ptx, this must be y. Now I will just explain later why we're gonna use y for ptx and x for pty. That's because of the moment arm. Now here, a will cancel, and so we are left with ptx equals ty divided by this expression. Now usually, if you are asked for the moment of inertia of a bolt group, this is the expression that you will use, especially in steel design. However, in mechanics of deformable bodies, you need to use this formula in the calculation of the moment of inertia of the bolt group. And so you have to remember this one. And so going back, we need to first find J. Now recall that J is the polar moment of inertia. Now for bolt groups, that's just gonna be, instead of Ix plus Iy, we'll just need the transfer formula. So this is gonna be x squared plus y squared. And so to get these values, we need to look at the horizontal distances from this point up to the center of the bolts, and also the vertical distances from this point up to the center of the bolts. So for distances along x, we have 166.67 squared from here up to here. And then we also have 83.33 for this bolt and also for this bolt. So we can just multiply that by 2. So we have 2 times 83.33 and then squared. Again, this is 2 because we have 2 bolts that have this distance from the centroid. And then we'll also add y squared, or the summation of y squared, because essentially this is the summation of x squared and y squared. This is what you have to remember. And so plus, for bolt A, the distance from this point up to the center, that's 200, the vertical distance, or y. So this is 200 squared, and then plus, for bolt B and bolt C, the distance from the centroids of the bolt up to the center, that's 100. And so we have 2 multiplied by 100 squared. And so our polar moment of inertia will be 166.67 squared plus 2 times 83.33 squared plus 200 squared plus 2 times 100 squared. And so this is 101,666.67, and then this is and then squared. Now for the first question, we need to compute the reaction of bolt A in kilonewtons. And so how are we going to solve this? Let's try to consider bolt A. So let me copy this. And so we know that PDY is 61.54 kN. And we also know that PDX is 25.64. However, we still don't know PTX and PTY. And so how are we going to solve that? Now to solve PTX, we have T multiplied by Y, because for PTX, our moment arm is the distance along Y divided by J. And then for PTY, we have T multiplied by X divided by J. And so let's try to look at bolt A to identify Y and X. Now let's first identify YA. And so here, the vertical distance from bolt A up to the centroid, that's gonna be 200. And so our YA is 200 mm, and then our XA will be the horizontal distance from A up to the centroid, and so that's gonna be 83.33 from here up to here. So 83.33, and then essentially for bolt A, this will have components PTX and PTY. And so notice that the moment arm of PTX is 200 mm going to the center, and the moment arm of PTY going to the center is 83.33 if we'll look at the perpendicular distances. And so that's why here for PTX, we'll need to multiply by Y, while for PTY, we need to multiply by X. And so solving PTX for the bolt at A, we have our T is equal to 80771.02. So let's copy this one. And then our YA is 200 mm divided by J, which is 10166.67. And so the unit of this is kN while this is 200, and then this is squared. And so squared will cancel, as well as these. So we are left with kN. And so our resulting unit for PTX, that's gonna be kN. And so PTX will be 80771.02. Now let me just store the values. We have 80771.02. Let me put this into A. So this is stored at A, while J will store this into B. And so 101,666.67, we'll store it at B. So this is now A times 200 divided by B. So this gives us 158.89 kN. And then for PTY, let's just copy this. And then this is now Y. And so what we're gonna change is this distance.
because we need x. And so xa is equal to 83.33. So changing this one, we can now solve pty. So this is going to be a times 83.33 divided by b. This gives us 66.2. So 66.2, and this is kn. And so this is now 66.2, while this is 158.89. Now since we are interested in the reaction of bolt A, then we need the singular equivalent force for these four forces. And so to get RA, or the reaction at A, this is going to be the square root of the forces along X plus the forces along Y. And so RA will be the square root of, for the forces along X, we have PDX minus PTX, because this is going to the left and this is going to the right. So they have opposite directions. And so 158.89 minus 25.64, and then squared. And then we'll add the forces along Y and then squared. So the forces along Y are 66.2, which is downward, so minus 66.2 plus 61.4. 54. So this is squared. And so solving RA, we have the square root of 158.89 minus 25.64 squared plus negative 66.2 plus 61.54, and then squared. So this gives us 133.33. And so this is our answer for number 1, which is letter D. And so now for the next problems, we'll just repeat the same process, but we'll now consider bolt B. So let me just copy this one, and then let's just modify these values as well as this one. So again, our PDX is 25.64, and then PDY is 61.54, and then we're gonna solve for PTY and PTX. So let's look at YB and XB. And so let me remove this. Let's look at bolt B. Now for bolt B, the vertical distance from the center of the bolt up to the centroid, that's 100 mm. So YB will be 100 mm. And then our XB, the horizontal distance from bolt B up to the centroid, that's 83.33. And so these are our values. However, since our XB is still 83.33, then this won't change. However, since this is now 100 for our YB, this now becomes A times 100, or you can just simply divide this by 2. This is now 79.45. So 79.45. And then here, for the reaction, let me just copy this one. So this is now B. This is also B. And so for the forces along X, let's try to look at our bolt. PTY is equal to 66.2, while this is 79.45. And so for the forces along X, we now have minus 25.64 because this is going to the left, and then minus 79.45 also going to the left. And then here for the forces along Y, we have minus 66.2 plus 61.54. And so this gives us square root of minus 25.64 minus 79.45 squared plus minus 66.2 plus 61.54, and then squared. And so this is 105.19. So RB equals 105.19 kN, which is letter D. And so for the last question, compute the shearing stress of bolt C, we need to first find the reaction at C. And so this is bolt C. And so we will still follow the same process. So let's just copy this one. This is now YC and XC, and this is also RC. And so looking at bolt C, the vertical distance from this point up to the centroid, that's 100, while the horizontal distance from this point up to this point, that's 166.67. So this is 100, while this is 166.67. And so this is going to change. This is now 166.67. So our PTY will be A times 166.67 divided by B. This is 132.41. However, this didn't change because our YC is still 100. And so now this is 61.54, this is 25.64, while this is 132.41, and then this is 79.45. And so here, we now have, for the forces along X, this is minus, and this is also minus, because they are going to the left. So minus 79.45 minus 25.64 plus the forces along Y, which are 61.54 going up, plus 132.41 also going up. And so RC will become 220.59. And so notice that RC is the largest among all the bolts. This is only 105, while RA is 133.33, but this carries the largest load. As what we have discussed earlier, the most stressed bolt is the bolt wherein the directions of PT and PD are the same. However, we want the shear stress of bolt C, and so in this topic, we have this formula. R is equal to 0.75 FVN, wherein FVN is the shear stress multiplied by the area. So this area is pi times 25 squared divided by 4. This is the diameter of the bolt. And then this is only our reduction factor. So this is now to 20.59. And then let's convert this to newtons so that we can get FVN as MPa. So times 1000. This is equal to 0.75 times FVN multiplied by pi times 25 squared divided by 4. And so solving FVN, we have 599.18. So FVN equals 599.18. And then this is MPa. And so this is our answer.